In this video, we're going to look at connecting the cell potential and delta G and K. So electrochemistry, equilibrium, and thermodynamics all come together in this last lecture in our whole AP Chem series. The amount of work that's available from any chemical process is maximized at delta G naught. So delta G naught is the maximum amount of work that's available. Now from physics, we know two things about work. One is that power is the ratio of work to time. And we also know that power is current times potential. P equals IV, you might remember if you've ever taken an electricity class or a unit on electricity. So let's set these equal to each other because both of these are power. So work over time is equal to current times potential. And I'm just going to use V for potential here. And because I want to relate delta G to all this electrochemistry stuff, I'm going to multiply both sides by T to get an expression for work. So work is equal to I times T times the potential. But I times T, that's charge. And the potential in an electrochemical cell, that's just the standard cell potential if you're at standard conditions. So this becomes work is equal to Q times standard cell potential. But remember that charge is equal to the number of moles times the number of moles for a coulomb, which is Faraday's constant. So that tells us that work is equal to number of moles times Faraday's constant times the standard cell potential. But work is equal to delta G. Now let's think about the signs here. Delta G is less than 0 if work is available. In other words, if it's spontaneous. But also it's true that cell potential is greater than 0 if the reaction is spontaneous. So these have to be opposite signs. So we can't just say that delta G is equal to N times Faraday's constant times cell potential. They have to be opposites to each other. And so we get this relationship. Delta G is minus N times Faraday's constant times the cell potential. Now I put degrees on here, the little standard symbols. So I have standard free energy change and standard cell potential. So we've just established that delta G naught is equal to minus N times F times E naught cell. But earlier, in a previous video from a previous unit, we discovered that delta G naught is also equal to minus RT times natural log of K. So let's equate these two because they're both equal. So minus N times Faraday's constant times standard cell potential is equal to minus R times T times natural log of K. The negatives can cancel from both sides. And let's solve this for standard cell potential. So standard cell potential is R times T times the natural log of K divided by number of moles times Faraday's constant, if we divide both sides by number of moles times Faraday's constant. So that's a relationship that gives us a standard cell potential. Now let's think about what if we're not at standard conditions. So we know from our study of thermodynamics and equilibrium that delta G is equal to delta G naught plus RT times natural log of Q. We have this equation from previous studies. And we know that delta G naught is equal to minus N times Faraday's constant times E naught cell. So just delta G would just be negative N times Faraday's constant times E cell, but not with the standard symbol on it. It's not at standard conditions. So let's substitute. So delta G is minus N times Faraday's constant times the actual cell potential. Delta G naught is minus N times Faraday's constant times the standard cell potential plus R times T times the natural log of Q. We want to know what the cell potential is under some non-equilibrium, non-standard conditions. And so let's solve for cell potential by dividing both sides by minus N times Faraday's constant. So that gives us cell potential equals, NF is going to cancel here, standard cell potential plus R times T times the natural log of Q divided by N times Faraday's constant. But this was a negative number. Now, one thing that we can think about here is that R is a constant Temperature is a constant, unless temperature changes. And Faraday's constant is also a constant. So we can separate all those constants out and evaluate them. So this is what we come up with. Remember, this is a negative sign because we were divided by negative n times Faraday's constant. And then if we put all those constants together, R is 8.314 joules per mole per Kelvin. And let's say we're at 298 kelvins for temperature. And Faraday's constant is 96,500 coulombs per mole. Moles are going to cancel. Kelvins are going to cancel. So we're going to get joules per coulomb. But a joule per coulomb is a volt. And if we multiply and divide here, find out our answer, we get 0.0257 volts. So with these constants separated out, this equation becomes cell potential is standard cell potential minus 0.0257 volts over N, which is the number of moles transferred, times the natural log of Q. Now lots of people prefer this to not be a natural logarithm expression. So there are math tricks that you can do to convert bases. And if you want to know how to do that, I mean, I can explain that to you, or you can consult with your pre-calc textbook. But when we do that, we find out that in the base 10 log version of the same equation, cell potential is standard cell potential minus 0.0592 volts over number of electrons transferred, number of moles of electrons transferred, times the base 10 logarithm of Q. This is the version I'm going to use as I solve problems. You can certainly use this one if you want to. It'll work just as well. Let's do an example problem. We have a zinc-copper battery constructed like this line notation shows, and it's 25 degrees C. And the question that we're being asked here is, what is the cell potential when this cell is first constructed? So the reaction is going to be zinc plus copper 2 makes zinc 2 plus copper, because this is anode and this is cathode, half cell. 2 electrons are transferred because both of the ions are 2 pluses. So N here is going to be 2. What's the standard cell potential? Well, we have seen earlier that when zinc is oxidized to zinc 2 plus and releases 2 electrons, the oxidation potential, standard oxidation potential here, is positive 0.76 volts, because the reduction potential for the reverse reaction is negative 0.76 volts. Remember, you can look that stuff up in tables. And we also saw that for the reduction of copper 2 by gaining 2 electrons to make just copper, the reduction potential, standard reduction potential, is positive 0.34 volts. So that means the standard cell potential, E naught cell, is 1.10 volts. It's the sum of oxidation potential and reduction potential. So what's Q here? Q is equal to concentration of zinc ions, which is 0.10 molar, divided by concentration of copper ions, which is 2.50 molar. And this works out to 0.04. So our cell potential is standard cell potential minus 0.0592 volts over 2, because that's the number of moles of electrons, times the log of 0.04. Standard cell potential, remember, is 1.10 volts. So when we calculate this all out, our cell potential is 1.14 volts. Next, we want to know what's the cell potential after 10 amps flows for 10 hours in this voltaic cell. And we're assuming 1 liter of solution volumes. Well, we're running out of space here, so we're going to switch to a different spot where we have more room to work and solve this problem. So previously, we had calculated that the cell potential when this was first constructed is 1.14 volts. And the question now is, what's the cell potential after 10 amps of current flows for 10 hours? So let's calculate this out by, first of all, figuring out how many moles of each of the 2 metals have been either lost or gained. We'll do that with dimensional analysis. So it's been 10 hours. We know there's 3,600 seconds in every hour. The current is 10 amps, so that's 10 coulombs of charge flowing every second. There's a mole of electrons for every 96,500 coulombs. That's Faraday's constant. And then there's 1 mole of each of our two metals, let's just say metal, for every 2 moles of electrons, because these are both 2+ ions. And if we calculate this out, we get 1.87 moles of either zinc 2+ or copper 2+. So what's our concentration of zinc at this point? Well, it was originally 0.10 moles. We're getting more zinc because it's being oxidized, more zinc 2. So we're adding our 1.87 moles, and that gives us 1.87 moles of zinc ions. And how about copper? We're getting less of this. We started with 2.50 moles, and we're losing 1.87 moles. So we end up with 0.63 moles. So Q is now actually I made a mistake. I forgot to add 1.97. Q is now 1.97 moles of zinc over 0.63 moles of copper ions, which is 3.13. So our cell potential now is equal to standard cell potential, which remember is 1.14 volts, minus 0.0592 volts over 2 electrons get transferred, times the base 10 logarithm of our Q, which is now 3.13. And this works out to 1.08 volts. The next question is, what's the mass of each electrode after the 10 hours occurs? Well, the mass of copper is going to go up by 1.87 moles times the molar mass of copper, which is 63.546 grams per mole. So the copper went up by 119 grams. So that means its mass is, there was originally 200 grams, plus 119 grams, we now have 319 grams of copper. Zinc, because it's being oxidized, is going down in mass by 1.87 moles times the molar mass of zinc, which is 65.409 grams per mole. That's 122 grams. So the final mass here is 200 grams minus 122 grams, and that ends up being 78 grams. Final question here is, how long can this battery last before it goes dead? Well, it's going to go dead when one of two things happens. Either we have oxidized all the zinc and there's no zinc left, or we've reduced all the copper too. So let's test it both ways. When the zinc is all used up, all 200 grams of it will have been used up. Remember, zinc is 65.409 grams per mole. There's 1 mole of zinc for every 2 moles of electrons, 96,500 coulombs for every mole of electrons, and 10 coulombs per second was our current flow, and this gives us 59,000 seconds. All right, so that's if zinc is the limiting reactant here. What happens if we run out of copper 2+? Well, we started out with 2.50 moles of it in our liter of solution. There's 2 moles of electrons for every 1 mole of copper 2+. This is moles of copper 2+ that were in the solution. And then 96,500 coulombs per mole of electrons, and then 10 coulombs per second for our current, and this gives us 48,250 seconds. So we will run out of copper ions before we run out of zinc, and that's how long the battery will last before it dies. Our last topic in this video is something called a concentration cell. This is a voltaic cell where both half cells contain the same components, which seems weird. It seems like that can't possibly be a voltaic cell, but it is if you just mess with the concentrations a bit. So here's a question. What is the cell potential for this concentration cell? So we have silver and silver plus in one half cell, and we also have silver plus and silver in the other half cell. So the oxidation is occurring here, and the reduction is occurring here. remember that cell potential is equal to standard cell potential plus 0.0592 volts over the number of electrons transferred, which in this case would be 1, times the base 10 logarithm of Q. But our standard cell potential here, that's going to be 0 because the oxidation and the reduction are the same, just opposite sign. So the reason we have a cell potential is only based on the fact that Q is not going to be equal to 1, and that makes this term have some value. So let's calculate it here. Cell potential is equal to 0, that's a standard cell potential, plus 0.0592 volts over 1 times the log of Q. Now we have to know what Q is. So it's the concentration of silver on the product side divided by the concentration of silver ion on the reactant side, and that is 1 over 0.1, which is 10. So we're taking the log of 10 here to calculate our cell potential. Log of 10 is 1. 1 divided by 1 is 1, so our cell potential here is 0.0592 volts. Now you might think this might be just a chemical curiosity with no practical value, but it actually does have some practical value. And here's a way of understanding that by looking at this particular cell. On this side we have a hydrogen electrode on the oxidation side, and we have a hydrogen electrode on the reduction side. So we are both oxidizing H2 and reducing H plus in this reaction. On this side, we have a 1 molar concentration. On this side, we don't know what the concentration is, and maybe we want to find out what that concentration is. So let's think about the cell potential here. First of all, the standard cell potential is 0 because it's the same half reaction on both sides. But cell potential is equal to standard cell potential minus 0.0592 volts over N, which will be 1 electron in this case, times the base 10 logarithm of Q. Now what's Q? Q is equal to the concentration of H plus on the oxidation side, the unknown side, divided by the concentration of H plus on the other side, which is 1. So Q is equal to the concentration of H plus. Now, if we take the log of Q, going back to this equation, we're taking the log of Q, we're really taking the log of H plus concentration. Remember, this is 0, so we can rewrite this as cell potential, which is something we can read off this voltmeter, is equal to 0.0592 volts over 1 electron transferred, in this case, times the negative of the base 10 logarithm of Q, which is H plus concentration. But what's the negative base 10 logarithm of H plus concentration? It's pH. So the cell potential is 0.0592 volts times the pH. So the pH is the cell potential divided by 0.0592 volts. So what we have just created here is a pH meter by dipping the left-hand side electrode into a concentration of H plus that we don't know and reading the voltage and then just calculating, and then we can just calculate the pH by taking the cell potential, whatever we read up here, and dividing it by 0.0592 volts. Now there's lots of these kinds of probes that are made, and real pH meters that you buy and use in laboratories are a little more complicated than this, but they work off the same basic idea.